All right, so let's pick up where we left off here with this 2.5 kilogram mass attached to the horizontal spring. Okay, so our givens so far, we've got mass 2.5 kilograms. We have an amplitude, which is really just the biggest that x can be, of 0.800 meters. And a spring constant, so that's K, of 40 newtons per meter. All right, they want us to calculate the acceleration of the mass when it is at a displacement of 0.3 meters. All right, since this is a horizontal spring, what's the only force acting on the mass? The restoring force, exactly. Okay, so that means that the restoring force in the spring is the net force. Okay, how do I calculate net force? M times A, right. How do I calculate restoring force? Negative kx. All right, so now I can calculate acceleration because I have k. They told me x is 0.3, and I have the mass. So I'm just going to divide both sides by mass, okay, and that'll leave me with acceleration. So I'll have negative 40 times the x, which was 0.3. And then I'm going to divide that by the mass, which was 2.5. All right, so its acceleration is going to be negative 4.8 meters per second squared. Okay, reason that its acceleration is negative is because it was displaced the other way. Okay, the displacement they gave me, they didn't give me a direction on it, but I just assumed it was positive because they didn't list it as negative. So my acceleration is in the opposite direction. Okay. How am I going to get the maximum speed? Where does that occur? At equilibrium, right? Okay, so the maximum speed occurs at equilibrium. So anytime I've been asked to calculate speed, it's been an energy thing. Agreed? All right, so I need to do a conservation of energy calculation in order to solve part B. That means I need information about two different points in the oscillation. And they give me that because they told me the maximum amplitude where all the energy is potential. All right, so I'm going to have 1/2 Ka squared, right, equals 1/2 mv squared. Now I could write x there as well, but they told me what the maximum amplitude was, so I'm going to leave it as a. So I'm going to divide here off and try and calculate the maximum speed, okay, of the object. So I'm going to divide both sides by half of m. All right, the halves will cancel, and then I just have to plug in my number. So K was 40, the amplitude was 0.8, and I'm dividing that, sorry, and that has to be squared, and I'm dividing that by the mass, 2.5 kilograms, and then I'm going to square root that in order to get V. Everybody okay with that? Again, the most common mistakes here, forgetting to square things. So we got 40 times 0.8 squared, okay, divided by 2.5. All right, so the, oh, sorry, then I'm going to square root that. All right, so the speed of the object, maximum speed of the object at equilibrium is 3.2 meters per second. Everybody all right with that one? Okay, and then the last part wants us to find the period, which I can find because I have both m and k, which are part of the period formula for a mass on a spring. So period of a mass on the spring is 2 pi times the square root of m divided by k. So 2 pi times the square root of 2.5 divided by 40. All right, so we should have a period of 1.57 seconds for that one. Everybody all right with that? And so expect that you could very often get a question in this unit that would involve you doing calculations from 3 different concepts or 2 different concepts for sure. Okay, I want you guys to try number 2. Don't worry about 3 or 4. Just try number 2 for now. All right, give you a few minutes on number 2 and see how you do. All right, so in question number 2, okay, we're given the mass. The mass is 0.0026 kilograms, okay, and it has an acceleration of 20 meters per second, okay, at a displacement of 0.700 meters, okay, on a spring. So we're looking for K for that spring. So what kind of question is this? Right, it's Kx, so that's whose law? Hooke, right? This is a Hooke's law question. So we're going to have that the force in the spring, the restoring force, is equal to the net force. All right, that's going to be negative K times X equals M times A, and we're going to be solving for the spring constant. So we're going to divide both sides by negative X, leaving us with K. So we have 0.0026 times 20 divided by negative 0.700. Okay. Now we're going to get a negative number here for K, but what do we have to remember about K? That it can't be negative. All right. They didn't give us a direction for this displacement. Okay. So we obviously aren't going to have a negative number. But here's the thing we do need to remember. In fact, we shouldn't get a negative number if we remember this, and even I forgot it. Acceleration and displacement, can they be in the same direction? Nope. If I displace it to the right, the spring is pulling it to the left. Okay, so this acceleration, okay, either this 0.7 is negative or the 20 is negative. Either way, I've got 2 negatives and they'll cancel each other out. Okay, as long as I recognize that. If I forget that, then I'm going to get K for a negative and go, oh, whoops, I did something wrong. K can't be negative, and I'm going to shake it off and say, oh, I got by that one anyway. Okay. All right, so when we do that, we should end up with 0.0743 newtons per meter, okay, as our answer for that one. All right, now I'm going to put up the worksheet that's got some Hooke's law and energy questions on it, but before that, I'm going to give you a couple minute break here, okay, and then that'll give me time to find it and whatever else. Okay. All right, let's have a quick look at number 3 here, guys. So on question number 3, they're telling me the mass of the object is 0.6 kilograms, okay, and that the restoring force is 1.2 newtons, right? They're telling me the displacement of the object is 0.025 meters. We're looking for the spring constant. All right, so if I know the restoring force, okay, I know that this is going to be involved. Everybody okay with that? Okay, and I know what that equals because they told me what it equaled. So do I have enough here to get the spring constant from this formula? Yes, I do. As long as I divide negative X over to the other side, okay, I should be all right. So I'm going to take the spring constant, which was 1.2, and divide that by 0.025. Okay. And then I should get my 48 newtons per meter. Right, 1.2 divided by 0.025. Whoop. Come on, turn on. 48. Okay, so it's just a Hooke's law manipulation, but the tricky part of this one is I almost never give you the force directly, and I threw mass in there to mess with you because, well, I'm that guy who just does stuff like that. Okay, so sometimes the question is going to give you something you don't use, and that's what I threw that in there for.
Could you go for number 5?
Number 5, yep. All right, so we have a 5 kilogram mass, okay, and it'll stretch a vertical spring 3.25 centimeters. Okay, so if it's a vertical spring, what's pulling against it? Gravity. All right, so we got negative kx equals m times g. Okay, and that's the trick to this one. The other trick to this one is they gave me the x in centimeters, and I need the x in meters. which is 0.0325. All right, so if I'm manipulating here for k, I divide both sides by negative x, right, and I'm going to have the k equals 5 times 9.81 divided by negative 0.0325, okay, and this should be another negative here because it's down, and that'll give me my positive k of 1,500 newtons per meter. Any other ones giving us trouble? 7? All right, so this one is talking about it vibrating on the end of the spring. So this time it's actually moving back and forth. So it could be a conservation of energy question. It could still be a Hooke's law question, right? So we've got a spring constant here of 26 newtons per meter. Maximum displacement, so in other words, amplitude, is 0.15 meters. We're looking for the speed of the object at equilibrium, which is where the maximum speed occurs. So this is the law of conservation of energy question because I have to compare these two places in order to make this work. So the maximum amplitude is going to be all potential energy, and at equilibrium, it's all kinetic. All right, so to get the maximum speed, I divide both sides by half of m. The halves cancel, and then I square root to get v. So v will equal 26 times 0.15 squared divided by 0.6. And when we do that, we should get 0.99 meters per second. Okay, so again, guys, as I'm reading through the question, I need to decide, is it a Hooke's law question or a conservation of energy question based on the context and based on what it gives me. Any other ones giving us trouble? Okay, keep her going then.